As we continue with systems of equations, we're going to talk about two algebraic methods. It's just how you solve these without looking at graphs, okay? And so the first one we're going to look at is something called the substitution method. It gets its name for a reason I'll explain in a moment. We looked in the last video at this system of equations, y equals 2x minus 1 and y equals negative x plus 5. And after graphing that, we found that the intersection point was the point 2 comma 3. Okay, so the solution we already know to be the point 2 comma 3. I'm going to leave that over to the side for a moment, and I'll kind of explain the substitution method, run through it, and show you that it is going to match up with the point that we found before. So what happens is at the intersection point, we had a graph, that one of those lines is increasing, one of those lines is decreasing, and we had this point of intersection. Well, at every other point, if I took an x value, back here somewhere, the output, or maybe let's put one right here, the outputs, there's going to be two different outputs, right? Each function gives me a different output for a given input, except at the intersection point. At the intersection point, both functions give me the same output, okay? So that's the only one in which the output is the same at both. If they're the same at both, then the y values and the x values for each function are the same. And things that are the same in equations can be substituted for each other. And so if the y value in one equation is equivalent to the y value in the other equation, and it corresponds to equivalent x values, then we can substitute one y for the other y, okay, or one x for the other x. It actually doesn't matter which one we use. In this example, I'm going to substitute the expression 2x minus 1 in for the y in the other equation. And the reason I'm going to do this, like I just said, if two y's are equal to each other, then, or if two things are equal to each other, then you can substitute one for the other. And of course, these things would all then be equal to each other, right? So we have 2x minus 1 is equal to y, which is equal to y, which is equal to negative x plus 5. And so all I have to do is make that substitution so that 2x minus 1 is then equal to negative x plus 5. Okay, so that's kind of the theory behind it. And then we solve this equation. Now there's only one variable. The ultimate goal of these algebraic methods is to reduce the equations down from two variables, x and y, to one variable, either x or y. Okay, here I've got x, and then I just solve this like I normally would a linear equation. So I might add the x to get my x's all on one side. That'd give me 3x minus 1 equals 5. And then add the 1 to both sides. 3x equals 6. And then divide both sides by 3. And I will have an x value of 2. Okay? Now remember though, we're not finished when we get an x value or a y value, one by itself. We have to get the full ordered pair. It has to be the x and the y together. So I take that number, the x value of 2, and I plug it back in to either equation. Remember, the output is going to be the same either way, so it won't matter which one I use. I plug it in and then evaluate. So I'm just going to go to the top equation. Again, it won't matter. The only thing that might matter is the ease of arithmetic. Okay, so sometimes you'll choose one equation over the other because it looks like the arithmetic will be easier. That's it. Other than that, the output will be the same. And so here, I simplify. I get, 4 minus 1, which is a final value of 3. And again, even now, I don't have a final answer. I just have two individual numbers. I don't have a solution set until I put them together and put them in the set. And so at this point, I would take the 2 and the 3, put them in an ordered pair, surround it with set notation, and I have my final solution set. Okay? And again, it does match up to what we found before. So the substitution method works. I'll go through a couple more examples. The other examples I want to show you, I'm not going to put the equations in slope-intercept form. They're going to be in standard form, and so you're going to have a little bit more work to do to simplify or to substitute. Okay, so let's try and equate a system. Let's go with 2x minus y equals 5, and x plus 3y equals 6. I think that'll work. Kind of making this up on the fly. So that should work. Should work out to be a nice number. Now they don't always work out to be nice numbers, but I'm trying to get them to come out to be nice ones. So, okay, so substitution method. In this case, I have all 4 of the variables, both x's and both y's, are on the left side of the equation, but none of them are solved for. None of them are by themselves. In order to do the substitution, you have to get one of them by itself in order to replace it into the other equation. It doesn't matter which of the 4 I choose. I can use any of them, okay? However, I think it might be nice to solve for a variable whose coefficient is 1, okay? Or -1, I suppose. If I were to solve for, let's say, this y, for instance, I'm going to have to divide out this 3 at some point in the equation, or in the solving process, and that's going to create some fractions potentially. Okay, same thing with this 2. If I were to solve for the x, I eventually have to divide by the 2, and then it creates fractions or decimals. What I might try instead is to solve for either this y or this x that have coefficients of positive or -1. Okay, I like the x here because its coefficient is +1. It's just going to be simpler to solve for. But again, you could solve for any of them if you're willing to work with the fractions and decimals or whatever else will show up. The answer is going to be the same either way. So let's go ahead and we'll solve for this x. So I'm going to work with this one. We're going to subtract the 3y from both sides. Again, this gets our x by itself, cancels out the y terms. X is going to be 6 minus 3y. Okay. Now the order of those two terms doesn't matter. You could do -3y plus 6. Won't matter as long as you don't combine them because they're unlike terms. And now I've got this expression that's equal to x. Okay, so this guy right here, this is not my answer. I'm just boxing it in so you can see it more clearly. 6x minus 3 is equal to x. Well, because the x's are the same in the two equations at the intersection point, I can replace the x in the first equation by the expression from the second. You always go to the other equation. Okay? So this x is going to replace the other x. So we're going to get, instead of 2x minus y, we're going to get 2 times an expression minus y equals 5. So this is the what I would call the structure of the first equation, where x is kind of removed, and I'm going to put this expression in for it. Okay, so this becomes 6 minus 3y. Again, I'm substituting, that's where the name comes from, substituting 6 minus 3y in for the x in the other equation. Okay. Notice now I only have one variable, I only have a y. Okay, so here I can solve for that y by distributing the 2. I get 12 minus 6y minus y equals 5. Combine my like terms. 12 minus 7y equals 5. I want to move the 12 to the other side. I'm going to subtract 12 from both sides. I get negative 7y equals negative 7. And then I'm going to divide out by the negative 7. And negative 7 over negative 7 is 1. So I have the y value for my answer. But remember, we're not done. Just because we got an answer or a number doesn't mean we're done. We still have to find the x. We need the full ordered pair. So I've got y equals 1. I then take that 1, replace a y in one of the original equations. It doesn't matter which one again, okay? But it has to go back to an original equation, and that will give me the x value. So let's take, I'm going to box that in. We'll do a little color coordinating here. And I got to move around the board. So I could choose either equation. I'm just going to go with the top one. I don't really know that either of these is easier than the other, so I'll just go to the top one here, and we'll go with 2x minus parentheses equals 5. The y I put in as a set of parentheses, and then this 1 is going to go in the place of the y, so yet another substitution. And then I can just simplify and solve for x. So it's 2x minus 1 equals 5. Add the 1 to both sides. 2x equals 6. Divide both sides by 2. And x will equal 3. So final answer now. Now I can finally get to a final answer. I'm going to combine the x and y values into an ordered pair. 3 comma 1, because you got to go x then y. And then I'm going to put them in a solution, or a set, okay, to be a solution set, right? Okay, so that gets me, it's quite a bit of work, but it's not too bad, because in the first step, you're essentially eliminating one of the variables, and so then you can just solve a linear equation from there. Okay, let's try maybe one more example. So let's try one more example. We're going to go with something like 4x minus 6y equals 10, and six x minus 9y equals 4. Let's go with this one, okay? So here again, I want to solve for one of the 4 variables, but in this case, none of them have a leading coefficient. None of them have a coefficient of 1 or negative 1, so they're all going to be kind of messy to solve for. That's okay, we just go ahead and do it and deal with the fractions or decimals. I am going to choose probably this 4, the x with this 4, because it's the smallest coefficient, and so when I divide, I'll just have 4s in the bottom, and I'd rather deal with quarters than ninths or sixths or anything like that. So I'm going to solve for that x. I'm going to take this off to the side. 4x minus 6y equals 10. I'm going to, if I'm solving for x, I got to get rid of the y term. So I'm going to subtract the 6y. 4x equals 10 minus 6y. Divide by 4. Now when I divide by 4, on the right side, it's going to distribute to both terms. So as long as you are dividing everything by 4, you can split it up that way. Okay. And then I'm going to simplify all those fractions. So my 4's cancel out. I get x equals 10 over 4 reduces to 5 halves. So I'll write it as 5 over 2. 6 over 4 reduces to 3 halves. So I'll write that as 3 over 2 times y. Okay, so just kind of simplifying those fractions a bit. Now this expression is equal to x, and so I'm going to substitute it to the x in the other equation. Well, I already worked with the first equation, so now I got to go to the second one, okay? So the x here is going to become my parentheses, and then in the parentheses I'm going to put this expression of 5 over 2 minus 3 over 2y. And here I'm going to then distribute the 6, solve for y. I've only got y in the equation, so it should work out nicely. 6 times 5 halves. Well, 6 times 5 is 30, divided by 2 is 15. 6 times 3 halves, well 6 times 3 is 18, over 2 is 9. Okay, so it becomes minus 9y. I did make a mistake. I'm wondering if you saw that. Right here, when I added the 6y to both sides, I didn't. I put a subtraction. That should have been a plus. I got to change my signs all the way down, and right there. Got to make that change. And I got to put the change right there as well. Okay? So, I did make a mistake. Hopefully I'm not making too many of those on these videos, but occasionally it'll happen. So I fixed it. It's good. I caught it because, well, I know what the solution is going to be, and it wasn't working out that way. So here I get 15 plus 9y minus 9y. Well, plus 9y minus 9y is 0y, right? So this ends up really being, those add up to 0, so it's 15 equals 4, and I've lost all my y's and all my x's. Well, that seems strange because 15 is not equal to 4, right? So this is a weird scenario. Remember in a previous video we talked about the two types of systems that don't have just a single answer. We had some systems that have infinite solutions and some that have no solution. This one happens to have no solution because at this point I have two numbers equal to each other that aren't actually equal to each other. Okay? So because these are not equal, we have a no solution. The variables dropped out. I have a false equation. Okay, so this is a false equation. And when the variables drop out, you have a false equation. That implies you have no solution. Okay, and therefore the solution set is going to be the empty set, right? So that's what we would have for a solution set. Now, remember we named these systems. The other systems we saw had solutions. This one does not, and so this is called an inconsistent system. And remember, inconsistent systems where there's no solution have parallel lines. Okay, so just to give you a review of that. Hopefully you recall that when we did have one solution, the other examples I just showed you, those systems are called consistent and they have independent lines, okay, or independent equations. Okay, so the other thing I wanted to mention is that, you know, this is a no solution example. If you had infinite solutions, you would have a similar situation where the variables drop out of the equation, but you would have two numbers that were equal to each other. Something like 4 equals 4 or 0 equals 0 is probably more commonly the case. When you have a true equation and no variables, then you have infinite solutions. Okay, so that's the other situation.